Hello, everyone. Welcome to um, the Data Science Mentor session. The Data Science Mentor program is for anyone learning data science from scratch, from data science to machine learning, starting from scratch, and learning using examples and mentorship. It's typically a guide through your learning curve. My name is Pablo. I am the founder, host, and convener of the Data Science Mentor program. So welcome. If this is your first time, then that means there are other resources you need to watch, and you can also drop your questions in our private Telegram channel. So welcome. Right, so today we are continuing from the last time. Just let me set up we're continuing from our last session. This is the 17th session, and that means we have been taking different steps. Right, and so what I'm going to do is I'm going to just do a little recap. Last time we started out multinomial Bayes, naive Bayes. This is what it is, which is more like a word counter. It has some assumptions, right? And I'm going to talk about those assumptions again. But what we did was to access, we do some text classification, and we just fetched some data. And you can see so we have a list of what we fetched. And the idea is to create some categories, train these categories, and see that if you were to extract certain text or a set of text or characters, it can predict what kind of category those characters belong to. Now we've been able to convert our strings to vectors, and so we're about to get started on this. But before we do that, I like to share another intuition. I think intuitions make a lot of sense, and I think it's massive. I think it's massive that we share these intuitions as we proceed. So here is another intuition for the multinomial naive Bayes algorithm. So here is, I'll just write this as another intuition. Now remember that for machine learning, we are trying to solve problems. The world that says all activities that happen in the world, they, whether we know it or not, they sort of like, you know, they sort of morph into some kind of a distribution. Depends on how you eat every day. Some distributions have become, obvious. Some distributions take a lot of observations to figure out. So we're going to look at the naive Bayes, the multinomial naive Bayes, and talk about one of the intuitions and one of the assumptions of this algorithm. Now, one of its intuition goes thus. All of the intuitions are features are assumed. Did I spell that correctly? No. Features are assumed to be generated from a multinomial distribution. This is one of it. So let me put this in quotes. Now, this is going to be the basis of what I'll talk about today, and then we go on to continue with what we were doing from our last session. Now, if this is your session, you've not seen the 16th session, and I think the 16th session here is the naive Bayes classification part 3, where we did the intuition for naive Bayes, one of the families of algorithms in the naive Bayes classification um, algorithm. So we're looking at the multinomial um, Bayes, naive Bayes. So just check it out, right? You can check out my YouTube channel. It could be, if it's streamed there, well, that's great. But if you are signed up to the Data Science Mentor Program, you can see just behind me, the Data Science Mentor Program. There you have access to these resources. So first, one intuition, features are assumed to be generated from a multinomial distribution. Now, what does that mean? What it means is features are counted from different outcomes. So like features, and then when we say features, what we mean is like word counts, click counts, purchase counts, stuff like that. These features are counted of different. Features are counted. Sorry, not counted. Are counts of different outcomes. So now you think about every time you do stuff, these things they happen, right? And every time you count all these activities, they come from a distribution. And these distributions grows out of how often they occur. So which means if you went out to buy maybe pizza or something, and when you went to buy pizza the first time, when you went to buy, say, shawarma or something, you bought a certain type of shawarma, there's a count for it, right? And that count for buying that's an outcome. Now, if in 6 months you buy shawarma consistently and you have different what do you call that? Different types of shawarma you buy. Maybe you buy beef, you buy chicken, you buy a combo. Now, whatever it is you get, the category it occurs in has a distribution. And by collecting this consistently, you would basically have something called a probability distribution. That is what it is. So how many times these things happen without you knowing them, and the outcome of what you do, you have a probability distribution. And this probability distribution is going to be checked, and categories, a lot of what happens can be predicted from the categories they fall into. So if you think about what you would do if you went online and sort of the clicks you would have if you were on a social media platform, how many times you went into a certain channel or you followed someone else, and that person has a certain, there's a thing about this user. What are the chances that you would also follow some other user that's similar to that user, right? So that's basically what we're looking at here. So if the features are count of different outcomes, and another thing we can say is that these counts come from a probability distribution that models how often each category occurs. So that's one intuition we're looking at here, right? And again, I just used the pizza one, I use the shawarma one. If you think about it in terms of customers, we use applications. If you're on a social media application, how you follow different users, right? Now, if we connect a lot of these activities, right, Now, what you have are data sets of either word counts, click counts, purchase counts, activity counts, and all that, right? So if you can make sense of the probability distribution, which is um, every time something happens or an activity happens, we have this assumption that these counts are from, you know, are from this probability distribution, which is, how many times they've occurred. Now, with multinomial distribution, where multiple categories compete for probabilities, right? Wherever they compete for wherever they end up forming a count, right? That adds up to a certain total. So if you're the type that would get into Twitter or X and you just go fit it to a certain user, there's a consistent count on how many times you do it. And different users click on different accounts and or different influencers. And these counts all sum up to the probability distribution. Based off of this, right, we can now make a prediction of what certain users are all about. Look at that. So, but we in this situation we were using texts, right? And we did this text here. You can see that this text has a bunch of stuff in it, and we're going to now work on what this text is about and go on to see what we can do from this, right? We already have the model. We already have the model here. You can see we have a pipeline which has a vectorizer that converts the strings to vectors, and then we have the multinomial naive Bayes, which is the model we're going to be building, training the model, training the data on, right? And so that's the assumption we're working with. Now, so we have done this in the other session, so we're just going to continue from here, right? So which means by the time we're done, we should be able to take a part of this text, right, and predict the type of category they belong to. See this? So that's basically what it is. We take as part of this text and predict a category they belong to. So again, if you think about what folks type on social media, can you take a portion of the text they type and use a model to predict the type of user you have? So these are different ways to look at it. Now, the next I'm going to do, since I have the model, this is the model already, which is basically a pipeline. What I'm going to do is I'm going to fit the model to our training data. So again, this is our training data. You can see that I have the training data here. You can also see that we have a test data. So train data, I just copied this. And when I put it here, I could basically just call this test. And you can see what the test data looks like. And so remember, assays, we are basically going to put them in different ways so that we have the target vectors and we have the feature matrix itself. And this is what we're going to do. Now from here, I'm going to now take the model and fit the model. Now remember, the model is a pipeline, so which means it can perform different activities, right? So which we can train. We can train the data here, and we can have the train. We can have the train dot targets. Yes. And then with that, we can now get the labels. When we get the labels, what we can now do is say model dot predict, and we'll predict using the test dot data. That's what we're going to do here, and then we'll run this. Now we already have this. Now, the many things we're going to do with this, what we have, and I want you guys to know that if you have seen this last session, I created a category of different setups, like, you know, conversations around science, computer graphics, religion, different conversations. And we are typically going to, use these categories to see how our model was able to categorize them, right? By looking at this, the model should categorize them and say, okay, we know what the different categories they belong to. Now, what we are going to use is we are going to use a confusion matrix. We are going to use the confusion matrix. Now we're going to use the confusion matrix to just a bit. Hold on, guys. Yes, so sorry, I was just trying to get some information. So we're going to use the confusion matrix to make sense of what we've done. Now I will use the confusion matrix here. I'm just going to extract that, say from sklearn matrix. We're going to import the confusion matrix here. Now we're going to see what this is about. So what we can do is we're going to take the confusion matrix. Now the confusion matrix is it's used to check, is a performance metrics to see how well the prediction, how well the model performed on new data. In this case, by looking at the different categories, how it was able to classify each category based on the word count and how it's been used, and based on a multinomial distribution, right? Just like I explained earlier. Now, what I'm going to do now is I'm going to call this, what do I call this? I will call this matrix underscore analysis. Let me call that the matrix analysis. And I'm just going to take the confusion matrix, and I'm going to now put inside the confusion matrix, I'll put my test dot target, and then I'll put the labels. So what I have my test targets, and I'll put the labels, which is how it is, the predictions is done with respect to the test targets, with our test target here. And so I have that here. Now I want to do a few things. I want to visualize it. So I'm going to import data visualization, data vis models. So I would import Seaborn as SNS. I would also import matplotlib .pyplots as PLT. I'm going to use this too because we need to visualize and look at how it had performed. Now we've done this. I think I have this. Yes, I should have this. Next thing I'm going to do, I'm going to use a heat map. A heat map will basically break down um, what we've done. A heat map will basically break it down, and I'll show us the different labels using the color combinations to tell us, how well they performed in terms of classifying uh, what we've doing setting up this classification. Now, I don't know if we have talked about classification. I don't know if we have talked about the confusion matrix, but again, it's a performance metric. Um, it is used to confirm what they call it has four outcomes. It has four outcomes. This outcomes are spread into different ways. It's going to predict positivity and to predict negativity. So it's like uh, true positive, true negative, false positive, false negative. So if you think of it this way, that we have done like a COVID test, right? We run a COVID test, and when you run a COVID test, there are two possibilities. The person has the disease, which is positive, and the person doesn't have the disease. The person doesn't have COVID. So you're going to test positive for COVID. You're going to test negative for COVID. Now, a true positive is when the patient tests correctly. When the test says, not the patient, but the test says you have COVID. And indeed, you have COVID. Now, a false positive will be to test wrong when the test wrongly says you have COVID, but you don't. That's the false positive, right? So let me write it down. So just to make sense of it. So what we're going to be using is the confusion matrix. Just figured, yeah, let me just say confusion matrix, and I'll just write intuition. And so that's what we have over here. So the intuition is pretty simple. The question will be, or the situation will be, you are testing, you're testing for COVID, you're testing for COVID-19 using the test kit. Right. Now, here are a few things that have to come out. Here are the two possibilities. So the person either has COVID, the person either has COVID, which is positive, or not, which is negative. Now, here are the few situations that are common, right? So when you have it, it's positive. You don't have it, it's negative. But now the test could be weird, right? So right after the test, you have a true positive. And so these are the things that the confusion matrix checks. So you have a true positive, and the tests correctly says you have COVID. Second, we have a false positive. The test wrongly says you have COVID. However, but you don't. That's the whole idea. You don't. So that's a false positive. Then we now have the false negative. And the false negative, the test wrongly says you don't have COVID. So that's false negative. Test wrongly says you don't have COVID. But the reality is you do. It happens. You go for a malaria test or something. Like, oh, they tell you, look, you have malaria, but you don't. So yeah, that's a false positive. Now, a true negative is when the test correctly says you don't have. So the test correctly says you don't have COVID. You don't have COVID. Now, so that's basically what this confusion matrix is about, right? And basically, what we are trying to get most of the passes true positive and true negative, and depending on the situation, and also try to check how our model performs when they don't get it right. So that is what we are going to do with what our predictions from our what we have. So basically, we have created this matrix analysis. We have created the matrix analysis. So let me bring this down here. So let's take this down here. Yes, we've created this matrix analysis. The next we are going to do is I'm going to have create a heat map. Right, so I'm going to now say sns.heatmap. Now inside, I'm going to say I'm going to put up my matrix analysis, and then I'll transpose it. And when I do, I'm going to say put out a square, and this square is basically what we want to put out for our heat map. Then we are going to, use we're going to use different we're going to check out a few things. We are going to make use of here or use FMT, which is we're going to format our code with when adding annotations. So we're going to use say FMT equals to D. Then we're going to we have a color bar, which is a normal stuff here, but we don't want a color bar. We'll just put false. Then we're going to have our X tick labels, and with our X tick label, we're going to say, let me make this work. With our X tick label, we're going to call this our train dot target names, and then with our Y tick labels, I hope I can destroy it. Yes. And with our Y tick labels, in here we're going to say we're going to put the same thing with this train here. We're going to put this here. And then we can now say color map, which is our C map. And our C map will be blue. If at this point you don't know what the C map is, you should check out the introduction to our data visualization. Now with that, we can now say plt.x label. And in here, we're going to call this the true label. Then we have plt.y label. And here we're going to call the predicted label. So, here we're trying to look at what's predicted. and what is actually true. So we say the predicted label. Again, this is all trying to look at how well we've done. Then we can now say plt dot show. So we'll run this. Okay. What do I do? Oops, sorry. What do I do? Oh, people. What is this? Model matplotlib.pipe has no attribute x label. Just a little mistake. Apologies. Right. So now you can see that on this side of it, we have our predicted label. Let me just make this it's easy to see. We have our predicted label and we have the true labels. Right now, with our predicted label and true labels, there's some missing. Something missing. Hold on a bit. There's something missing. String. Okay, let me see. I would love to have. I'd love to have numbers to this. But then, basically, you can see that I want to have numbers to these, and I'm trying to wonder where did I get this wrong. We have our labels, we have our test targets. Let's see this. Is true. Why don't we have our numbers? Apologies, guys. We are supposed to have numbers to this. So, how do I do that? Okay, let me make. We're supposed to have numbers to this. Something is missing here that's supposed to show that we have numbers. Something. Yeah, look, okay, so if true, write the data values in each cell. Oh, I see. Let me put this now. We're going uh, to annotate. So I'm going to annotate and I'm going to say, when we annotate, I'll put true. Let me see if this works. Okay, then we'll run this. Oh, nice. Now you see that these are the predicted labels, right? And remember that when we use for all of them, we have the true, we have the true positive, we have the true positives. Hold on, let me see. True positives, false positives, right? True positive, false negative, false positive, true negative, right? So these are the things we have here. So basically, this is a breakdown that is like saying, look, you know, how were these things predicted, right? And so you can typically see what the predictions look like for the darker ones. The darker ones are telling you how well they try to predict. Now you can see something here. We have sock religion. You see what did with these predictions here. Now there's something about these two things, and you can see that it's talk religion and and this religion. So they sort of now are really close to each other, right? And this now makes it's pretty an interesting position, but what now makes it make a lot of sense is when we now choose to now do the prediction itself. So what we're going to do is we are going to create a very simple function, and this simple function just makes us determine the categories we're working with. So I'll say define pred underscore category. And inside, we're going to take three things. We should have we take S and which is they're typically like the characters we have. Then we'll have train, and by default, we're going to put our train in here, and then we'll have a model, and by default we'll put the model we have. So whenever we don't call this model, what's just going to happen is it's going to use the default. Then what it does here is that we have our pred, and inside our pred, what we would use will be our model dot predict, right? Our model dot predict, and whatever we give to it is S, which will be in here, and we'll put that. So it's going to be like a list that we'll put in here. Then we'll now go on to return. And when we return, we're going to say our train dot target. That's what we're going to return, our train dot target names. And when we return our train dot target name, we would use pred and say, please let us know what you predicted. So that's what we're going to do. So we have the pred category that will take in the characters, by default taking our train, and then which is our train data, then the model, and then predict the target name. So we'll run this. And so which means if I say pred category, and I now come over here, look at these data points here. I just come to this place and maybe say Madeline O'Hara and 8 is to eliminated, and I just put this here. And of course, it should make sense of, because I just came to the data itself, but I'm going to try something else when I'm done. Right. So if I run this, what did I do? That's weird. What did you say? Okay, let's try something else. Contaminated. Was this supposed to be like? Okay, so let me, from where I got this from, let me just take something from there. Maybe that will work. So let me try this here. This should work here. Okay, so something is wrong. The list object isn't callable. Why isn't it callable? So we have pred, we have train. When it's not callable, it means we probably didn't do something right. Let me see. We didn't do something right. If it's not callable, the list is not callable. Whenever stuff like this says not callable, it means we wrote a code somewhere and it's supposed to be a list, but we did not put the right stuff. And lists have to be callable. This is the return. Oh my goodness. Then let me go back here again. And just to pull this out again, I just wanted, this is the training data. We typically would use something else, but just to be sure, right, that we have this going on. Right, so we put this here. It keeps telling us we did not segment it properly. Do you want me to put this here? Okay, let me use something else. Um, maybe the categories we can pick out from. Uh, let me please go ahead.
There's an apostrophe in OR. I think that's what is affecting the distance. So you should use double quotation.
There's an up. Oh my word! I promise you, I didn't even see that. Imagine I even missed that. So in that sense, I should use this. I was wondering where the hell that was coming from. Oh, look at that. Thank you so much, Israel. Right. So you see that at this point, it's 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 able to do this, but this isn't even the conversation we want it to, because this was extracted from the data itself. So it's easy for you to figure it out. We can say stuff like the computer graphic design. Look at that. So you see or we can basically say stuff like, because remember, if we come back here, we have, yeah, look at what we have. There's 4 guys. And so there's some like, there's a conversation around religion. I can say something like, Jesus resurrected in after 3 days. That, or we can say stuff like, what's that conversation? Maybe I just say stuff like Judas. See? But you can see that the reason why 2 of them have similarities is it could have as well been Judas and Jesus went to the synagogue. Now I'm just trying to now bring so 1 minute just Judas alone is thinking it's talking religion, then now it goes it's Christian, right? We can say a lot. Just imagine what it would say if we said prophet. What does this say? It's religion. Okay, so again, this we can just typically do some prediction, and it's basically from the multinomial naive Bayes that we use to run this, and this is basically a hands-on level. Now, the naive Bayes classifiers, make really strong assumptions about their data. They will generally not perform as well, as more complicated models, but they have their advantages. They're easy to interpret. They provide, very good probabilities, because they look at how many times this has probably been used in, and it just says, look, if it's been used several times, then there's a chance. There's this probability distribution that if it keeps showing up on one category, it's probably what it is, right? So they have advantages. It's often really good to use to use like these Bayes classifiers, for baseline if you want to do any classification, right? So there are many things, right? So there are, again, remember, these things make it easy for us to do predictions, right? And they help out in a lot of ways. This way, that means that you can, use this to maybe understand customers and the kind of things they like based on what they have done in the past, even though it sees them as independent. But by the time you can check click count, you can check what a customer, the kind of things they type on a social media platform, what you think they're talking about, You can predict their type of mentality and stuff and place them in certain categories that would make other, users of a social media platform either want to be friends with them or follow them and stuff like that. But I like to use these intuitions a lot. Although this one I just mentioned is a lot more than that, but I want to put intuitions together that makes it make some sense. So yes, so that's what we're doing with this. So this today, we use this to just complete the deep dive into this work we're doing. We're going to do a couple of deep dives, and we'll be done with the machine learning part of things, and that will be the end of this first cohort of the data mentorship program. But the next deep dive we're going to do is we're going to look at a simple linear regression. We've looked at naive Bayes classifiers. We look at simple linear regression. Maybe one more. Maybe like we could look at decision trees and random forests, or maybe we could look like support vector machines. But again, the idea is, remember, don't be so about the tool. It's about the craft. It's what you want to use. There are assumptions for these models. They have assumptions, and it's ideal you think about the real world problems, how these real world problems behave. They have patterns, and using the right model that has basically the great assumptions that are close to what you're trying to solve makes you extract some insights you probably never know existed. So yep, that is that for today. Right, if you have questions, feel free to ask. If you are watching this again, or you're watching it for the first time, it means you're not watching it during the live session, then you are watching a recorded session. So please feel free to drop a question in the Telegram channel.